while we undertake this journey related to polynomials, quadratics, equations, and so on and so forth, here's one problem which will send out loads of instruction to you, which will bring in semblance of maturity. Take a look at this problem. Not difficult, but in a certain sense I do like this problem. Have a look at this problem. X, Y, Z are real numbers such that x plus y plus z is 4, x square plus y square plus z square is 6, and we want to be able to find the interval in which x, y, z lie. Now obviously, with two equations you will obviously not be able to solve for x, y, z, but it would be possible for you to estimate the interval in which x, y, z lie, right? And the other thing is, all three lie in the same interval. Doesn't spring a surprise at all, because these two equations treat x, y, z on equal footings. Why? Because you can interchange x with y, y with z, z with x. All kinds of permutation combination you can carry out with x, y, z. But these two equations are agnostic, unaffected, and inert towards those changes. So good. What I'm going to introduce to you is a little bit of a different strategy towards solving this problem. How to produce an inequality that would be satisfied by an x or a y or a z. First things first, let me try and get rid of two of the three. Let me try and construct, for example, a quadratic whose roots are y and z, right? So, equation whose roots are y and z, what's that? A quadratic equation whose roots are y and z. That's going to be t squared minus t into y plus z plus yz equal to 0, isn't it? And in this, let me remove y and z with whatever I have at my disposal. Now y plus z is not difficult to eliminate here, because y plus z is 4 minus x, which I can write in terms of x, not an issue. So this is like a t squared minus t into 4 minus x. And then yz, what do I do with yz? Yz I can write as half of y plus z whole squared minus y square plus z squared. Right? I could do this. And what's y plus z whole squared? Y plus z whole squared is going to be 4 minus x whole squared. So that's going to be half of 4 minus x whole squared minus y square plus z square. Y square plus z square is 6 minus x squared. Right? So good for us. So yz is half of 4 minus x whole squared minus 6 minus x squared. Yes or no? What's the whole idea here? What's the whole idea? Some of you would have guessed already. It's a quadratic in t. T is a real number because t produces output like y and z. So t is a real number. So when you solve for t, you would get real numbers. So would you not expect the discriminant of this quadratic to be greater than or equal to 0 because t is a real number? Yes. Now the discriminant can be written entirely in terms of x. So d greater than or equal to 0 would lead you into an inequality involving x alone. And that might just be the thing we were looking for. Let's check that out. So d greater than or equal to 0, that is like a 4 minus x whole squared minus 4 into half into 4 minus x whole squared minus 6 minus x squared, right? That's the discriminant, greater than or equal to 0. Let's see what this leads to. So this is like a 4 minus x whole squared minus twice 16 minus 6, that makes it 10, and then minus 8x, and then there is a minus x squared plus x squared. So there is a x squared plus x squared, that makes it a 2x squared, greater than or equal to 0, discriminant greater than or equal to 0. This is what you get. Yes or no? 4ac. 4 minus x whole squared minus 6 minus x squared is like 16 minus 6, 10. There is a minus 8x and a x squared plus x squared, 2x squared greater than or equal to 0. Let's check this further. What does this produce? So I have like a x squared minus 4x squared, that makes it minus 3x squared. And there is a 16x minus 8x, so plus 8x. And there is 16 minus 20 minus 4 greater than or equal to 0. We are headed in the right direction, right? I'm sure you feel thrilled about coming to this step. Some of you would have already jumped to the final stage, final step, and would have drawn a conclusion. Eureka is what you would have said. A number of you would have said Eureka. All right, just to multiply with a minus sign, so minus 8x plus 4 less than or equal to 0. Now this is not difficult to factorize. 64, 12, 48, 16. The discriminant of this is a perfect square. So then, this is like a 3x minus 2 into x minus 2 less than or equal to 0. That's what we get. And then from wavy curve, put x equal to 3 by 2, 2 by 3, x equal to 2 by 3, and put x equal to 2, and then the wavy curve. This expression becomes negative when x lies in the interval 2 by 3 to 2. So x then belongs to 2 by 3 to 2. And whatever comes true for x will come true for y and will come true for z. Isn't it fun? Thank you so much. We'll share more of some stuff of this kind very soon with you. Bye. All right. We are virtually unstoppable. And I want to share more treasure with you. Nothing difficult, but only things that apparently look difficult, but deep down they are simple things. Another member of this category is what I'm going to share with you right now, right here. Check that out. We have a quadratic polynomial given by fx equal to x squared plus ax plus b. And one of its zeros means roots, is 4 plus 3 root 3 by 2 plus root 3, where a and b are integers. And we now construct another polynomial gx of degree 4, x power 4 plus 2x cubed minus 10x squared plus 4x minus 10, such that g of this means the value of this expression at x equal to 4 plus 3 root 3 by 2 plus root 3 is c root 3 plus d. We want to be able to find a and b. A and b are integers, c and d are also integers. Hey, so one thing, one of the roots of this quadratic is 4 plus 3 root 3 by 2 plus root 3, right? And a and b are integers and therefore rational numbers. So if one root is irrational, the other one must also be irrational and must be its irrational pair. Irrational roots occur in pairs. So first thing, we write this root alpha in terms of something plus an irrational number, rational plus irrational number. So alpha, which is one of the roots of this quadratic, is 4 plus 3 root 3 divided by 2 plus root 3. Let me multiply with 2 minus root 3 to rationalize this. 2 minus root 3. And that produces like, so this would be 4 minus 3, 1, and the numerator is like 8 minus 9, which is minus 1, and 6 root 3 minus 4 root 3. 6 root 3 minus 4 root 3 is like a 2 root 3. Right, good for us. So we know one of the roots of this quadratic, and therefore, since the coefficients are all rational numbers, the other root of this quadratic beta must be its irrational counterpart, minus 1 minus 2 root 3. Yes or no? And therefore, I can readily find this quadratic. This quadratic is like a x squared minus sum of the roots. Sum of the roots is minus 2 into x plus product of the roots. Product of the roots, as you can see, is 1 minus 4 3s are 12. Right? 1 minus 4 3s are 12. So minus 11, 1 minus 12 minus 11 equal to 0. And that's like a x squared plus 2x minus 11 equal to 0. Yes or no? That's the other root. See, I hope you understand this. I rationalize this. I got minus 1 plus 2 root 3 as one of the roots. The other root is minus 1 minus 2 root 3. Why? Because irrational roots occur in pairs. So minus 1, and then I have minus, I have 1 minus 4 3s are 12. 1 minus 12 minus 11. So x square plus 2x minus 11 equal to 0 is this quadratic. So very clearly I already know A and B. A therefore out of comparison must be 2 and B must be minus 11. B must be minus 11. Yes or no? Right? Now, look at this expression. I want to find the value of this expression at x equal to minus 1 plus 2 root 3. I want to find the value of this expression at x equal to minus 1 plus 2 root 3. So, what am I trying to do? I'm trying to obtain gx, which is like a x power 4 plus 2x cube plus minus 10x squared plus 4x minus 10. I want to obtain the value of this at x equal to alpha. That means at a value of x that satisfies this equation, because alpha will satisfy this equation. That means at a value of x that satisfies this equation. Yes or no? I want to obtain the value of gx at x, which is minus 1 plus 2 root 3 and therefore satisfies x square plus 2x minus 11 equal to 0. Yes or no? The value of this, given that x square plus 2x minus 11 equal to 0. And therefore the writing is on the wall. All that I want to do is, I want to be able to write this expression in terms of x square plus 2x minus 11. Because x square plus 2x minus 11 will always be 0. Let's take the way ahead. So, ordinary algebraic manipulation, x power 4, I bring from outside and I artificially inseminate this quadratic, x square plus 2x minus 11. The 2x cube, I don't have to manipulate anymore because it's already there. And there is a minus 11x square, so I'll have to bring a 10 plus 11x square minus 10x square. That's going to give me an x square plus 4x minus 10. I hope all of you understood what I did here. I took this x power 4, I wrote that as x square into x square plus 2x minus 11. This 2x cube which I brought from outside can be sourced from here itself, homegrown. And there is a minus 11x square that I brought from outside, so I added a plus 11x square minus 10x square, which is this x square, and there is a 4x minus 10, right? So this part automatically goes into oblivion and this becomes 0. And then what I have is this x square plus 4x minus 10, I can write this as x square plus 2x minus 11, and then I have like a 2x plus 1. That's how I write this. So that this x square plus 2x minus 11 once again becomes 0, and you're simply left with a 2x plus 1, where what is x? X satisfies this equation and corresponds to alpha. X is this, so which is like twice minus 1 plus 2 root 3. So that makes it minus 2 plus 1, of course, twice x, and then there is a plus 1. So minus 2 plus 1, that makes it minus 1 plus 4 root 3. That's the value of this expression at a value of x that satisfies this condition. So very clearly c must be out of comparison minus 1. This must be c, and what must be d? C is 4 out of comparison. C turns out to be 4, and what about d? D turns out to be minus 1. D turns out to be minus 1. There we go. What looked like a real monster with just about some clear, transparent thinking could reduce to such a simple problem. And that is what happens most of the time. Most of the time it's much ado about nothing. And this is one classic example where when you encounter this problem, you think, hey, this is so ugly, I'm not going to look at this problem. Let go this problem, you'll move to other problems. But realize that this was after all not as ugly as it looked prima facie. Thank you so much. More in a little while. Bye-bye. another very general problem which does not involve or require special knowledge, special skills, but it just looks different. And therefore, like I said, I don't want you to be indifferent towards a problem that looks different. Let's just go ahead. Be brave enough. Here's the problem. X squared minus x cos a plus b plus 1, which is a quadratic expression, is a factor of the expression 2x power 4 plus 4x cubed sin a sin b minus x squared cos 2a plus cos 2b plus 4x cos a cos b minus 2. We want to be able to find the other factor, right? Since this is a polynomial of degree 4, you have one quadratic factor, the other factor must also be a quadratic. Product of two quadratics will give you a biquadratic, which is this, right? So, 2x power 4 plus 4x cubed sin a sin b minus x squared into cos 2a plus cos 2b plus 4x cos a cos b minus 2. Right? This is the expression. This is the expression. And it's known to have one of the factors as x squared minus x into cos a plus b plus 1. That's one of the factors. So if one of the factors is a quadratic, you would expect the other factor to also be quadratic. Now, this space I need to fill up. And let me minimize the work. There is a 2x power 4 required and there is a x squared. So I know right here there must be a 2x squared because that's going to produce a 2x power 4. Now look at the constant term. I need a minus 2 here. I have plus 1 here. So the constant term must be minus 2. And then there is a middle term. Middle term is like some px, where p is the only unknown that I have to deal with. The problem has reduced to such a simplified version, such a straightforward simplified version. Now, very clearly, in order to, if you factorize something, what do you get? If you factorize something, you end up getting, is it an equation or an identity? No, it's an identity. This expression is identically equal to this expression, and therefore coefficient of equal powers of x on the left hand side must be equal to the corresponding coefficients on the right hand side. That means coefficient of x power 4 on the left hand side must be equal to coefficient of x power 4 on the right hand side. Coefficient of x cubed on this side must be equal to coefficient of x cubed on this side, and so on and so forth. That's what produces an identity. Alright, so what I do is, to be able to find p, let me try and equate coefficient of x cubed on both sides, right? So let me try and equate coefficient of x cubed on both sides. So when I do that, what's the coefficient of x cubed on the left hand side? That's simply 4 sin a sin b. What's the coefficient of x cubed on the right hand side? That's like, oh, so this into this will give me x cubed. So there is a p that is sitting here. And then where else? Then I have like a minus 2 cos a plus b. Minus 2 cos a plus b, that's also going to produce an x cubed. So minus 2 cos a plus b. Right. Yes or no? See, this into this produces x cubed. Px into x square also produces x cubed. So all that I've done is I've equated coefficient of x cubed on both sides. And there we have p as 2 cos a plus b plus 4 sin a sin b. Right. Now see, if I expand cos of a plus b, that's going to be cos a cos b minus sin a sin b. So that's like twice cos a cos b minus sin a sin b plus 4 times sin a sin b. So minus 2 sin a sin b plus 4 sin a sin b, that's going to be plus 2 sin a sin b. So then this is like twice cos a cos b plus sin a sin b. and which is like a cos A minus B. So that's like twice cos A minus B. Twice cos A minus B. Yes or no? So once again, you know, sometimes they will just bother you with bad looks of a given situation, but eventually you'll realize that those are actually very easy situations to deal with. Bye-bye. For your eyes only, another problem, and also for your mind. Let's look at this situation. We have A, B, C, D natural numbers, and that are commensurate with two conditions. A cubed plus B cubed is C cubed plus D cubed, and A plus B is C plus D, and A plus B is C plus D, right? We want to show that if both these conditions are met by A, B, C, and D, they can't be all different. They can't be all different. You can't have A different from B and C and D. You can't have a set of 4 distinct natural numbers A, B, C, D satisfying this condition. Again, like I said, the problem only looks different. It's not difficult. Let's see how to deal with this. So first things first, let's start with the A cubed plus B cubed is C cubed plus D cubed, which is like A plus B whole cube minus 3AB into A plus B equal to C plus D whole cube minus 3CD into C plus D. That's what we have, right? And very clearly, since A plus B is C plus D, A plus B whole cube will get cancelled with C plus D whole cube, and then we have A plus B also cancelling with C plus D, and then we have minus 3AB is minus 3CD, which means AB equal to CD. Good for us. So we have AB equal to CD, and we also have A plus B equal to C plus D given. Right. Now, look. Actually, you've solved the problem. If you've come to this point, you're already there with the solution. You just need to now look through what you have obtained. Not an extra vision, but it's like you can't overlook things here. Suppose AB is CD and say each is equal to P, and if A plus B is C plus D and let's say each is equal to Q. Each is equal to Q. Let me find a quadratic whose roots are P and Q. Right? Let me find a quadratic whose roots are P and Q, whose roots are, say, okay, P and Q. So right? So x square, or rather, let me find a quadratic. Let me find a quadratic whose roots are A and B, for example. Let me find a quadratic whose roots are A and B. So x square minus A plus B into x plus AB. This is a quadratic whose roots are A and B. Yes or no? This is a quadratic whose roots are A and B, right? And what does this reduce to? This reduces to x square minus A plus B, which is Q, QX, AB, which is P, equal to 0. This is a quadratic with roots A and B. This is a quadratic with roots A and B, x square minus qx plus p equal to 0. Let me find a quadratic whose roots are, so let me call this 1. Let me find a quadratic whose roots are C and D. What is C plus D? C plus D is also Q, so x square minus qx plus CD, which is p, equal to 0. Hey, it's just about interpreting these two. These are identical equations. The roots of this I claim are A and B, and the roots of this are C and D. Both these equations that are identical should produce the same set of roots, yes or no? Which means the set AB should be the same as the set CD, except that, you know, it may appear in different order, in the sense that if these two are the same pair, in the sense that we could have had either, so what are the various possibilities? A equal to C is one possibility and B equal to D, right? In which case they are not different, not all different. Or the second possibility is A equal to D and B equal to C. Yes or no? In which once again they are not all distinct, which means A, B, C, D are not all different. We will have either A equal to C and B equal to D, or A equal to D and B equal to C. These are the only possibilities and they are not different because AB and CD are the product of the same quadratic equation and therefore they can't be different at all. Yes or no? Bye-bye. This time we have an equation to solve. X power y power z into y power z power x into z power x power y is 5xyz. One equation, goddamn 3 unknowns, x, y, z. X, y, z are natural numbers. I want to solve for x, y and z. How on earth is that possible? All along you've been told 3 equations for 3 unknowns, but now you have 1 equation and 3 unknowns. But then you also have a supplemental condition that x, y, z are natural numbers. I want to be able to solve for x, y, z. How do I do that? How on earth am I going to accomplish that task? Alright, first of all, if nothing occurs, let me at least bring this x below this, bring this y below this, bring the z below this, and see what happens. Let me at least club the 3 together. That means x by x to power y to power z divided by x into y to power z power x divided by y into z power x power y divided by z. That means I have brought this x, y, z below this equal to 5. Equal to 5. And I'm sure you've started to think already, right? Let me just do a little more mundane manipulation. X power y power z minus 1, laws of indices, into y power z power x minus 1 into z power x power y minus 1 equal to 5. Right? Hey, yo, where does it go? 5 is a prime number. 5 is a prime number. And this prime number is expressed as a product of 3 other integers, 3 other natural numbers. It's expressed as a product of 3 other natural numbers. Good Lord. What do you do with this? Very clearly, the only possibility is 5, a prime number, could be fragmented into product of 3 more natural numbers. If one of them is 5, 1 is 1, 1 is 1. So either this is 5 and this is 1 and this is 1, or this could be 5 and this is 1 and this is 1, or this could be 5 and this is 1 and this is 1. We'll look at one case and then the rest you can independently handle. Let me look at a situation where this is 5, this is 1, and this is 1. And let me see where it takes us. Let's see where it takes us. Now for this to be 5, x power y power z minus 1 to be 5. The only way this could be 5 is if the power is 1 and if x is 5. If the power is 1, that means y power z minus 1 is 1, and if x is 5, that's the only way this could have been 5. Yes or no? Because x, y, z are natural numbers. So which means we must have x equal to 5 and y power z minus 1 equal to 1. That means y power z equal to 2. Y power z equal to 2. Oops, y power z, y and z are natural numbers. Y and z are natural numbers. How could y power z be equal to 2? The only way this could be 2 is if y is 2 and if z is 1. If y is 2 and z is 1. Therefore, we have a set in which X is 5, Y is 2 and Z is 1 causes this to be 5. But I want to check when X is 5 and Y is 2 and Z is 1, these should also be 1. Yes or no? How do you see this one? Y is 1. Y, this is Z power X. Z power X means 1 power 5 minus 1. 1 minus 1, 0. So Y power 0, that's going to be 1. Not an issue. How about this? X power Y. Now Z is 1. In this case, Z is 1. So this automatically is 1. So 5, 1, 1, which will give me X is 5, Y is 2, and Z is 1 is a solution. And similarly, you could explore other solutions by taking this 5, this one, and this one, or this 5, this one, and this one. Wasn't it an interesting situation which originally didn't look very appealing, didn't look very enticing, but surely it did offer some excitement. The solution was not as difficult as one might have anticipated given the prima facie look of this problem. Thank you so much. Bye. So, a problem on quadratics. C and D are the roots of x square plus ax plus b equal to 0. We want to be able to find the roots of x square plus 2c plus a into x plus c square plus ac plus b equal to 0. Now, this problem is more about a little bit of an observation than anything else, right? What's the observation that can come in handy here? Look at this. There is a x square plus 2cx plus c square. Do you realize x square plus 2cx plus c square would combine as x plus c whole square, right? So x square plus 2cx plus c square will combine as like a x plus c whole square. Now, there is a ax and ac. There is a ax and ac. So that you can write as a into x plus c. And then there is a b. There is a b here. B equal to 0. I essentially want to find the roots of this, the values of x that satisfy this. Now, look at this equation. X square plus ax plus b equal to 0. Do you realize, essentially, if this pops out a value x equal to c and d, when you solve for x, and if x turns out to be c and d from this equation, then from this equation, x plus c. See, because these two are exactly the same formation, What x gives you in this equation is what x plus c will give you in this equation. Yes or no? Or just compare. This is like something square plus a into something plus something equal to 0. So when you solve for something here, you get c and d. Now that something becomes x plus c here. Something square plus a into something plus b equal to 0. Now if you solve for that something x plus c will give you the same set of values, c and d. That means when you solve for x plus c, you get x plus c or d, or you get x equal to 0 or d minus c. That means the roots of this equation, 0 and d minus c. 0 and d minus c. So this is a problem that didn't involve any manipulation. All that it involved was looking at this expression with love and affection, right? And it obliged. This is it. Nothing difficult about this problem. Have fun. Bye-bye.